So in this one, I want to talk about second order homogeneous linear differential equations with constant coefficients. Hopefully, we know what all of the words there mean. The constant coefficient part is really the new part, and it's going to be again a narrowing of our focus to a special case, which is especially amenable to and tractable as something that we can really solve. But at the same time that it's very solvable, it's also extraordinarily useful, and we're going to see lots of applications and uses for this theory in the coming days. Okay. But yeah, let's talk about this. So we have here, we're talking about second, I'll write it all out, second order um, linear. Oh, wait, did I put the H before the L? I think I did. So maybe I'll write homogeneous linear differential equations. Oh my goodness. That is not how you spell it, but my body wants to stop writing things. Differential equations with constant coefficients. So remember that a general second order equation would be something like this. This is y double prime plus p of x, y prime plus q of x, y equals f of x. So this is what we call a second order linear differential equation. We can make it homogeneous by making the f of x there be 0. So this I would abbreviate as a second order homogeneous linear differential equation. And then finally, we are going to narrow even further to a situation where the p and the q are constants. Maybe I'll write it as instead of writing p of x and q of x, I'll just write p and q, shall I? So plus p y prime plus q y equals 0. In which case, I might say that this is a second order homogeneous linear differential equation with constant coefficients. Okay. Just to keep things understandable. So here, crucially, p and q are constants. They're numbers. Okay. They do not depend on the independent variable in any meaningful way. Yeah. Okay. So we are really narrowing focus here. And it turns out that when you narrow focus this much, it becomes pretty easy to figure out how to solve these things. And it breaks down into a number of cases. We're going to talk about a couple of these cases here in this set of videos and do some examples. We'll talk about some the one exceptional case, and you'll see what that is right quick in future videos. So here's the idea. The idea behind solving this. Solving in particular second order homogeneous linear differential equations with constant coefficients. Okay. Guess that y equals e to the rx, exp of rx is the solution. This is a highly educated guess because it turns out this works really, really well. And you're allowed to ask, why this? And the unfortunate answer is, I think, because it works. Yeah, it works. And that's a selling point in and of itself, right? If it didn't work, this would be a terrible guess. But remember, this is partially motivated by the theory that we've seen in the past. If we can find two linearly independent solutions, then we can get the set of all solutions by taking linear combinations of those two linearly independent solutions. So how we arrive at those solutions that are linearly independent That's entirely up to us. And a really good way of doing it is simply to guess, to make a really good guess. Okay? Um, Fortunately, once you learn this and you know how to solve this, we can mash them together to get every single solution, and then we can start using these in the context of where we're headed. We're headed toward a theory for what are called harmonic oscillators. So that's coming. But let's go ahead and make this guess and see what happens. Now, if y is equal to e to the rx, I know you know that y prime is r times e to the rx. And I know you also know that y double prime is equal to r squared e to the rx. Yeah? And now what we can do is plug all of this into our second order, this thing. Plug all of this into here. So we're going to take this, we're going to plug all this information here. We're going to substitute it into here. And what we're going to get out, oh, and let me erase some of these green arrows. We don't need those. What we're going to get out is, so y double prime is r squared e to the rx. That's y double prime. Plus p times y prime, which is r e to the rx. And then finally, we have q times e to the rx. All of this is equal to 0. Okay? So this is the result of me trying this solution, e to the rx, where r here, sorry, maybe I should have said this, r is just some constant, okay? Now, what can we do? How can we manipulate this equation here? Well, I hope it's very conspicuous that e to the rx is a common factor of all three of the terms here, so we should factor it out. And if we do that, we get r squared plus pr plus q, and this whole thing is equal to 0. Sorry, let me do that again. This whole thing is equal to 0. Now, what do we know about e to the rx? It's an exponential function. And in particular, an exponential is never 0. So it is perfectly legit for me to divide both sides of this equation by 0. And what we end up with is the equation r squared plus pr plus q equals 0. And this is like something that you could have encountered in high school. This is a quadratic equation in r. It's got an r squared there, pr. These are all numbers. P and q, remember, are constants. So this is a quadratic, not unlike something you would have seen again in high school or whatever. And you learn scads of ways to attack and kill an equation like this. We give this kind of equation here a name. We call it the characteristic equation. The characteristic equation associated to our second order linear differential equation with constant coefficients. This homogeneous, yeah? Good. Now, we solved this. So now, solve the characteristic equation. And I'll do an example in just a second, but just relax. What I want to say, though, is that we know something. We've been through this game enough in our lives that we know something about what's going on with the solutions to a quadratic. Okay. For example, you could and you can do this in any number of ways. Remember that you could factor. That's one way. You could complete the square. That's another way. But one way that I want to highlight is using the quadratic formula, right? You can use the quadratic formula. And associate it to this equation. Now, don't forget the good old quadratic formula. If you have something like ax squared plus bx plus c equals 0, it's always worth reminding yourself that x is, oh, shoot. Do I remember? It's negative b plus or minus the square root of b squared minus 4ac. divided by twice, 2 times a. Good. This is the quadratic formula. I know you've seen it in your life. You have to have. But now, how do we apply it here where what's playing the role of a is 1, b is p, and c is q? Well, if we apply that, what we get is that r is equal to, so negative p plus or minus the square root of b squared, that's p squared, minus 4 times 1 times q, divided by 2 times a. Okay? Now, we can compute this using the quadratic formula. And remember, there are 3 cases that are of interest here once you get this. That's not how you spell 3. 3 cases. The first case is if this number underneath the square root here, which we sometimes call the discriminant. It's called the discriminant because it discriminates between the following 3 cases. The first situation is when p squared minus 4q is positive, strictly positive. If p squared minus 4q is strictly positive, then that means that the quadratic formula generates for you 2 different roots. And I should say 2 different real valued roots. 2 real roots. And we'll call them R1 and R2. Okay? R1 and R2. That looks weird. R1 and R2. Sorry. R sub 1 and R sub 2. These are just numbers, people. Don't get all weird. These are just numbers, okay? And in this case, because remember, don't lose sight of what it is that we're doing here. We have made an assumption that the solution to our second order homogeneous linear differential equation with constant coefficients looks like e to the rx. And what we found is that that's equivalent to requiring that r squared pr plus q is equal to 0. Well, if p squared minus 4q is positive, then that means there are 2 solutions, r1 and r2, to this equation. So then backtracking, what does that mean? That means that for this choice of r1 and r2, for the choice of r equaling r1 or r2, we get a solution to this differential equation. And in particular, because r1 and r2 are distinct real numbers, because the discriminant is positive, we know that we have 2 different solutions. We have that, I'll write it like this. Y equals e to the r1x and y equals e to the r2x are solutions. To what? To the second order homogeneous linear differential equation with constant coefficients. Yes? Okay. Let me just, and in particular, because R1 and R2 are distinct, these are going to be linearly independent solutions. So in particular, this also implies that y equals C1 times e to the R1x plus C2 times e to the R2x is the general solution. Let me describe the other 2 cases, and then I'll end the video and we'll do an example. Okay? So second point. If p squared minus 4q is exactly equal to 0, this implies that we have 1 repeated real root. Just think about it, please, because if the discriminant here in the quadratic formula is 0, right, then we're plussing or minusing to negative p 0. So we get the real root negative p over 2. It's repeated, yeah? And if that's the case, we're going to have to do a little bit of work. And I'll try to justify this in a future video. But I'll say that The solution in this case is that y equals e to the r x. Oh, yeah, we should call the root just r. Y equals e to the rx is a solution, but so is y equals x e to the rx. In this special case, again, where we have a repeated root, we get this weird solution, x e to the rx as a solution, okay? And then finally, there's the situation where p squared minus 4q is negative. Very important, this. In which case we have what are called complex roots. And this requires a separate discussion as well. And we'll do that in future videos, focusing on complex numbers, okay? But let's call this video over, and in the next one, I'll do some examples of that first case there, okay? See you in the next one.